Thank you everyone for joining us for our BrainX community live session for May 2023. We are very excited to have two eminent speakers from Pathology. For the first time, we are having Pathology at our BrainX community live in the last 5 years since we started. And for those who don't know about BrainX community, we started this now 5 years ago with the idea of creating a platform for machine learning in healthcare for good. Now we have run 5 very successful years. Our membership has grown to be 4,000 plus international members, more than 2,000 members who are very active on LinkedIn. The website is listed over there, which has plenty of resources for you to get started or carry on with your journey regarding AI in healthcare. And of course, we do these monthly live sessions to bring in people who have done some amazing work and share their experiences here. This is our webpage. You can go there. You can find a lot of information and the latest information updates in our update section. We have the Connect segment, and this is part of the Connect segment. So even if you miss one of these live sessions, you will be able to get information about that, including the video on our YouTube channel. So record these, and that will be available to you on our YouTube channel. And the upcoming sessions are also listed with the information about speakers and the agenda. So please subscribe our YouTube channel so that once it's recorded, it'll directly be made available to you through that subscription. And as I mentioned, a very active LinkedIn group, which we went public with recently. And with that, we are able to share a lot of scientific information related to AI and healthcare articles, the scientific publications, meeting opportunities, and so much more. And then our popular Learn section, which has links to some of the latest and the greatest articles, so that if you want to learn what's new in publication world, you can go over there. They're categorized. There is a filter option, so you can filter it by your favorite specialty and look for those articles. And of course, our very popular data section, which has more than 150 links to open source datasets. Again, this also you can use with a filter, so you can look for your favorite healthcare specialty dataset, and we provide you the links. You can go directly to those data sets, and these are open source. So with minimum DUA, you should be able to get access to these. And again, our podcast series, which features experts who have done some amazing work related to AI and healthcare. You hear about the journeys, you hear about their passion, you learn about their work, and then you learn from their vision for the future. So any of your podcast channels, you can subscribe BrainX Talks and get our podcast there. Our meetings and conference section, now that COVID is done, hopefully you have the opportunity to connect in person, and that's what Dr. Gullapalli and Rashidi were talking about just a little bit ago. And you can look at these meetings which are focused on AI and healthcare and connect over there with us. With that, let's talk about pathology. Pathology amongst a lot of different healthcare specialties has been a leader when it comes to both the quantity and quality of publications. And that's what we want to highlight in this session today. And we also have our very exciting speakers, Dr. Hooman Rashidi, who is the Vice Chair of Technology, Innovation, and Computational Pathology at the Pathology Lab Medicine Institute, is Director of the Institute Center for AI and Data Science at the Cleveland Clinic. So he's my neighbor over here. And he's also going to show us some awesome Auto-ML platforms that he has built and some opportunities to collaborate in the future. And that will be followed by Dr. Rama Gullapalli. Dr. Rama Gullapalli is a physician scientist in the departments of pathology, chemical, and biological engineering at the University of New Mexico. He obtained his medical degree from the same med school as me. We were in the same class, and he was the brighter and the smarter one. He did some amazing training at Penn State University way before I even knew what engineering was. And he went on to become smarter, to do smarter and more exciting work at University of New Mexico. So he'll be talking about ethics. He'll be talking about applications of AI and provide us his perspective. So with that, I'm going to hand it over to Dr. Rashidi and have him present.
Okay, great. Thank you so much for that kind intro. And I'm going to share my screen with you. And there is my screen. So thank you for the invite. And for those of you who basically are on the line, I did post in some review articles in the chat box. So feel free to use that, because I do also believe in it. And those are some of our reference scores of our upcoming AI course in Cleveland Clinic. But I also believe in democratizing ML. So hopefully that will help with that mission. So with that being said, I'm going to basically get started. So the topic is synthetic data and auto-ML opportunities that will help transform medicine. And I do have some disclosures. A couple of things that I'm going to show you are based on some platforms that are that I've developed, and they are, one of them was intellectual property of University of California, which is around Milo's platforms, and which is a suite of different data science applications. So you'll see one of those apps in action with synthetic data usage. And then the second one is the newest thing that we have, which is the IP of Cleveland Clinic, which is called Sting, which you're going to basically, hopefully will enjoy seeing how Sting works in action. So with that being said, the outline of this talk will really be around what is synthetic data, exactly, what are generative AI platforms and how they basically kind of are similar and also different than your non-generative AI tabular data type studies. And then the subtypes of the tabular data studies and the synthetic data generations that we typically deal with. And then finally, Sting, the platform that can automatically build and generate synthetic data sets. So where does it all start? As you know, everything we do within AI and ML starts with the data. And because this talk is really, as I said, around synthetic, I'm going to be concentrating around mainly synthetic with maybe a little slight combination of synthetic and real, and the challenges that they face. But the story really revolves around different types of synthetic data. So one being generative AI like ChatGPT or DALL-E and Stable Diffusion and whatnot. Others around tabular synthetic data forms, so partially synthetic data in terms of, can we automate certain imputation processes as we clean up our data, real data? And then finally, what happens if we want easier access to fully fake data that truly emulates the real counterpart? And that happens to be our all synthetic data realm, where things like Sting can help, help move forward. But although these things share a lot of similarities, it's very important to note that they have distinct entities with marked differences, especially within medical applications. So not to be the same things should not be applied to one versus another, as you'll see why. So what I mean by synthetic data, by the way, is new data. So this is that mimics the property of the real data and often used for training and testing ML models, especially useful in scarce, sensitive, or costly to obtain projects. And this is a study that actually, a projection that Gartner put out for what they're predicting what's going to happen by 2030. And as you can see here, they're predicting that 2/3 of the data that we're going to be using in all fields combined are going to be synthetic, and 1/3, real data. So this is the projection moving forward within our data science camp. So our commonly seen synthetic data that we typically talk about are generative images or video. And this is kind of like a peripheral smear that was generated through Stable Diffusion's training. And so basically you can generate fake images of, histology or pathology or radiology report and whatnot. And then here's a custom chatbot that basically you could have created where it can actually do things that are very specific to your particular field. So rather than using a generalist chatbot. And then finally, generating tabular data, things that we typically deal with in EMR with many of our studies that we typically do. So many of our pilot studies are just tabular data that are basically extracted from EMR. But deep learning approaches really are the reason that there's a major revolution that has happened that basically has enabled us to move forward with a lot of these things, especially within synthetic data generation, as the stuff that I just showed you. And these are platforms that included, autoencoders, generative discriminator, kind of a generative adversarial networks, GANs, diffusion models, like I was just showing you, and now obviously the latest and greatest transformers, as you've seen, like with the GPT, GPT, and other platforms. But the main question you may ask is how to generate synthetic image data. And so the classic one is was Goodfellow initially brought up, which was the GAN platform, right? And this one is kind of incorporated between a GAN and a GPT platform kind of combined, as I've basically asked for this education talk to create me a robot that's holding a phone, and just to show that you can teach with, robots. But you could also build, these fake images through, other platforms, as we've done here with Stable Diffusion. So diffusion type platforms can do it. Synthetic text data is, kind of a variation on that theme, where as part of like a bigger generative AI foundation models, these are typically trained on a broad range of data that can adapt to various tasks, typically initially starting off as unsupervised and lead to more refinement and, reinforcement learning and kind of a supervised, customized thing later on. And then these things can lead to powerful platforms like OpenAI's ChatGPT or custom fine-tuned chatbots that you may actually use. And this is an example of a custom chatbot that we've used that actually can answer hematology questions, as I'll show you an example in a few minutes. So the generative AI versus tabular synthetic data generators, it's important to know that there are definitely similarities between them, because they can both uncover hidden patterns and relationships and whatnot, but there are marked differences between them as well too. So it's important to know that even though they're very similar in certain aspects, they're also very distinct entities. Generative AI, typically we're talking about things that deal with unstructured data, images, audio, text, although it doesn't have to be that alone. And the current LLM chatbots, though, are, even though they're very powerful, they're really built for general, studies, general tasks. They're not really made to do specific disciplines, at least not generally. So not very good at different medical disciplines, for example. So a solution around what that would be, you can take general chatbots and in healthcare and life sciences and build custom ones. And as I'll show you in a second. So these custom chatbots is basically a very similar concept as what we've been doing for 10 plus years, where you can actually do transfer learning, for example, on ImageNet type studies or neural networks. Let's say you took a ResNet and that was trained on cats, dogs, and cars, and now you trained it to identify cancer versus no cancer, and on a tissue. And so, or in radiology, images. And so the idea is similar, but they're not identical, but they're similar. So you can customize by doing some kind of a transfer learning approach or a variation of it. And so here's one where we've done a transfer learning, kind of like in this case here happens to be an ICL, which is an in-context learning, where we basically have a custom chatbot that's competing with GPT-4, the latest, greatest chat. And I'm asking it very specific questions in HemePath. So in hematopathology, I'm asking about ICC versus WHO criteria, and in myeloid neoplasms, and obviously it doesn't give me a good answer. It's all gibberish, actually. And so the idea is, this obviously does not meet my needs. Now, if I went into a custom chatbot that has trained on my own stuff, it gives me exactly what the main differences are based on the papers. It even cites my paper at the bottom of it. But because it's a chatbot, I can also ask it about things that I'm not familiar with, like diagnostic qualifiers. So I can say, well, exactly what do you mean by diagnostic qualifiers within this? And it basically tells me immediately that I mean that you have to include history of chemotherapy, radiotherapy, that sort of thing. So now I can learn more, again, being cited. And by the way, these are set at very low temperatures, like temperature is 0, so that it minimizes hallucinations too, as opposed to your general chatbots. Here's now another example where I asked it, you have a patient that has features of CMML2, but the GPT-4 gave the wrong diagnosis of AML or MDS. But if I put it in our custom chatbot, it gives us exactly the right diagnosis of CMML2 and the references. But I can also ask it, because it understands context, I can say, what happens if there was no monocytosis in this patient with the 14% blast, where in that case, obviously it completely changes the diagnosis to an MDS AML per ICC criteria. But it's also smart enough to tell me why it's done that, because it says I did that because you had 10 to 19% marrow with no monocytosis. So that's the other power of it. But it can also be done within templates that we built for, let's say, diagnostic templates. And many people have been, or wanting to start to use these. So this one happened to be a patient that I wanted to write a diagnostic report on somebody who has AML with 90% blast. Dr. Who reviewed it and agreed, Dr. No was informed. And if you put it in GPT-4, it doesn't give you the way we sign out these cases because it doesn't understand our template. It was never trained on it. But if I put it in our Heme chatbot, because I trained it around our template and it knows what a template looks like, it gives me exactly how I'm supposed to get it out. But plus, because I've set the temperature so that it doesn't hallucinate and it basically gives me the same exact results over and over, it also minimizes hallucinations because when I change the Dr. No to Dr. No Dat, it only changed the Dr. No Dat part and not Dr. No. So you can see the power of these things that could be in the place, but also keeping in mind that there are limitations to these platforms. So that was generative AI, just a quick glimpse of it. But what about non-LLM generation of tabular synthetic data, like unique features, limitations, and opportunities? And these are typically structured tabular data, like CSV type files that you would want to kind of like EMR type stuff. And most people are familiar with these things because also the validation statistical performances on these is more familiar to you than validation performances on an LLM, which on an LLM, you may be looking at perplexity score, and most end users won't know what that means. But within these ML type studies, when you're dealing with structural tabular data, let's say a classification scheme, you're dealing with accuracy, ROC, AUC, sensitivity, specificity, things that people are familiar with. So that's an important point to kind of distinguish. Types of synthetic data generation in tabular format, they can be partially synthetic, where you're actually have missing values, let's say in a real data set that many of us deal with regularly with, where now you're trying to replace those missing values in that real data set with imputed values or inferred values. And that's your classic imputation problem that we deal with. But what if you also have one that's all synthetic, where there is no real data whatsoever? They're completely distinct. They have a lot of shared similarities, but distinct entities. So we'll start off with partially synthetic tabular data, a mix of real and synthetic, so imputation specifically. So here's an example of a data set that I have with cancer, and it's a freely available public domain on a, the identified data set that basically looks at the cancer data set. And you see there's a bunch of missing values in yellow, and there's also columns that have text values, which the machine will not understand, both in the target and also in one of the features. And so there's some major tasks that you have to do in terms of cleaning up this data set, right? So taking care of the missing values, taking care of the non-numerical data like text, but there could also be a multicollinearity issue. Maybe you have duplicate columns or columns that have high collinearity. There could also be noise in there where maybe some of your features may not be contributing to your final model. So lots of stuff to do. And all of these, by the way, interplay with each other. So there, here's an example where you can actually use an automated platform to actually do the imputation, one-hot encoding, and the multicollinearity assessment and whatnot, all under one umbrella in an automated process. And one of Milo's tools, as I disclosed earlier, is able to address this. And in the big advantage to something like this would be that instead of something that would have typically taken us days to weeks to take care of, we can actually do them within minutes within this tool. And so this is how the tool works. So here's an automated pre-processing tool where that same data set that I showed you earlier was pulled in. And it's literally, if you can attach a file into an email, you can work within this data, this platform. And that data set had 697 rows and 2 columns. And the 2 columns basically for the target were negative and positive cases, which it automatically basically called them negative zeros and positive pos. And then it also shows you how many missing values you had. You had 15 negative cases and 9 positive cases that were missing values. So now the big question comes at this point is, okay, now you uploaded the data set, you looked at it, and how do you know which column or features in this cancer data set are contributing the most to your missing values? And so within these features that are the headers there, which one basically is contributing the most? Within the Milos platform, that's the step 3, where I can see that bare nucleoli happens to be the one that's most contributing to this data set. So in this pathology data set, I happen to, if I kept the bare nucleoli, I would have 24 missing values. But if I remove bare nucleoli, which I've done in this case, I now can go from 24 missing values to 10 missing values. So that also could be a good thing from a standpoint if I have to remove, the 10 or impute the 10, which I'm planning on doing here. And so are there any other columns that have text values, you would say? And how do you convert the text values to their proper numerical counterpart? And the classic thing that we typically do is one-hot encoding, as you may know. And this is an example where I have a risk column here of high, intermediate, and low. And within the platform in the step 4, I can actually just remove the risk column and do one-hot encoding and create 3 binary high risk, low risk, and intermediate risk columns instead, which takes care of the text to numerical conversion in this case. And how to best deal with the missing values, remove or impute. And obviously in this case here, we're talking about imputation. So I'm going to concentrate on that. And if you notice right now, it shows you where the orange bars are, like the missing values. They're a small subset are in the class 0 and a larger subset are in the class 1. And the way we've designed the system is that it will not let you impute in the generalization test set, which because we feel that's not good practice. So it forces it, if you do have to impute, you can only do it in the initial training, initial validation data set. And when you're splitting the data into the 2 separate test sets, that initial test set may have imputed values, but the follow-up secondary or generalization test set will not. And so then what about multicollinearity assessment in the middle of all of this mix of things that you're doing? And you may actually, on this case here, I can tell you that size uniformity and shape uniformity typically have very high correlations. But within the 6th step of this tool, you can quickly assess the correlation where you see that it's a high correlative, field, and you could actually mark those as, in this case here, I marked size uniformity and high risk to be removed because they had high correlations, one a negative correlation, one positive correlation. So in summary, here's the final summary of what it shows you what the initial data set started with, which was 1 file, then turned into 2 files that's now ready for your machine learning study. It had 24 missing values. Now it has 0 because you've imputed the stuff. And it also gives you the audit files in the bottom left in terms of seeing what you've done where. And here's the final result. It's a data set that's now ready to run. Now, so that was partial synthetic data assessment and cleaning, where obviously it's part of your real data set cleaning part. So that typically would take you time to get access to the real data set. And typically it's months of waiting for the IRB approval. But what if you needed the data now? You have a brilliant idea that you want to test right away for a quality project or whatever research study, and you just needed the data right this second. Well, obviously you can't have it right now because the real data would be under IRB approval criteria. But the solution can be the use of all synthetic tabular data, where that could expedite your IRB approval. And what exactly are all synthetic tabular data? And so as opposed, these are definitely not the same thing as the identified real data. So as opposed to the identified real data that can be re-identified, we're talking about new data here, meaning that your individual rows don't represent real patients. But collectively, the mathematical relationships are maintained so that the collective mathematical relationships of the synthetic data set matches the original real data set if all the right validations have been done in the proper place. So how do you acquire a fully validated all synthetic tabular data? Well, the best way around it would be you would have to have a platform that can be unbiased to the tabular synthetic data generation process, but also preferably have an embedded Auto-ML validation platform that can expedite the process and give you the best results possible, while assuring data privacy and data representation of the real data counterpart. So our solution to this ended up being STING, which stands for Synthetic Tabular Neural Generator. And so now imagine you're an investigator who have a great idea and you want to basically now test out your idea. Obviously, you need to access the data, but you'll need IRB approval for accessing the data for that real data set. Because real data set has lots of challenges to its name, right? Like HIPAA, but there's also public relation issues because patients may not feel comfortable having their data maybe shared between one institution and another, or between, let's say, one institution and an industry partner and whatnot. So a great solution around this would be, instead of reusing the real data, use the synthetic data counterpart. So, and the other thing is, since you know the vast majority of the studies that we do in healthcare space happen to be classification and regression tasks, and by far the most of them are classification tasks, then concentrate on something that also can have an Auto-ML validation that happens to be a classification platform. So our goal ended up being, after building an automated synthetic data generated sting that is able to do this around classification tasks. Now, but the big question you may ask at this point is this, which is, how do you know if the synthetic data that you now generated through Sting performs just as well as the real data? And our solution through Sting addresses that. And it's kind of in tune with one of these studies that we've done not too long ago with Amazon, like a few years back, which was using the real data built on the optimized machine learning model that gives us the ground truth. You then basically use the real data then to build the synthetic data counterpart data sets. You use those synthetic data sets then to build new machine learning models and see how well they do with synthetic data testing. But more importantly, you don't stop there. You now do tertiary testing with the original real data set as tertiary testing. That way, when you show initial validation, secondary validation, and tertiary validation showing you similar results, let's say similar ROCs, then you can be pretty certain that you're probably on the right track. So how does Sting achieve all of this? This is how Sting works. So imagine if you have a data set of like, let's say your clinician asks for 1,000 cases, let's say 300 sepsis and 700 no sepsis cases. Sting initially builds a pipeline of building an automated platform where it automatically builds, splits up the initial 1,000 cases into 2 separate data sets, builds, trains, and initially validates on an 80-20 split on the initial one with cross-validation, then does secondary testing. So you get a ground truth with 2 separate ROCs and various other performance measures on the real data. But it does the same thing now with the synthetic data after it's also turned the real data into the synthetic data counterpart. So the same thing you've done in the green, after you've now turned the real data into synthetic forms, you now can build machine learning models around that synthetic form as well and do the same thing you did in the green. But now the big difference is that the synthetically generated models now are not only tested once and then follow up twice on synthetic data set 2, they're now done tertiary synthetic data testing, real data testing on the real data set counterpart to see how well would they actually do in the real world situation. And then if they would perform well and you see all 3, let's say all 3 ROCs are nearly identical, and let's say they're all in the mid 80s, and then the likelihood of you having something by chance is way, way lower, then you can feel that that's a validated synthetic data set. And if they don't, then it becomes a non-validated synthetic data set. And obviously, in order to increase the chances of doing this, we actually run 8 separate pipelines, synthetic data generation pipelines simultaneously to increase the chance of getting a validated synthetic data set every single time. So in summary, not only it builds a multitude of synthetic data sets through synthetic data generators, it also runs and automatically finds the best machine learning model for your particular needs based on the initial ground truth. But then after it automatically builds the synthetically generated ML models, it does the tertiary testing on the real data set. And then that enables you to see if you basically, you have a data set that the synthetic data set that actually performs like the real data set or not. So here's Sting in action actually for you in this 2-minute video. So imagine you want to do a heart disease study on this, and an investigator is asking for this heart disease study from your, let's say, analytics or IT team. And so you now basically, as somebody in the background, you have access to the thing, your IT or analytics team pulls up the data, it's fully on-prem. And this one here, this is what it looks like. So you can see the pancreatic cancer, diabetes, and breast cancer studies that were done in the past. You now pull up the CSV file of the one that you have an interest in. That happens to be real heart disease. You pick the target so that does the classification Auto-ML for you too. In this case here was heart disease in a binary, but it could be multiple classes too. And you just upload it. Now in upload, you now see how many you brought in. You had 300 and some cases in here, some of them positive, some negative. You can see the various data distributions of the real data and see exactly what you had where. And now if you're ready, you can just say start the job. And that's it. Now everything is done automatically in the background. So that real data evaluation, I was saying the real data set automated machine learning process is done in the background in the top one. And then the gray one is all the 8 different synthetic data generators that are going to follow suit afterwards. Once the real data is done and it forms the appropriate models, then you get the performance of the real data. And it shows you here, you have an ROC of 86 on the secondary testing. But then the individual synthetic data generations, different neural network and non-neural network synthetic data generators, they're now going in place. And then the blue represents the secondary ROC for the synthetic data sets. And then the green is the tertiary testing. And so you can see exactly how close you are to the real when you compare to the far left real thing. And then you can also see exactly how they've performed on the real. And that we also have our own proprietary Sting score, which is basically a way to, not instead of visually to see which one is best. In this case, you can see Gaussian copula Sting is the best one. And so you could now, that matches what you've seen visually right there with the Gaussian copula Sting. And now you can actually go live with it and kind of see, dig into the data, see, what exactly it will do. And so this one, you can also expand the data set immediately. You can, instead of 1-to-1 ratio, instead of 300 cases, you can get it to create 1,500 cases, so 5 times as much. You can even do Auto-ML studies on the expanded data set, so you can see if expansion will help you or not. And it also shows you the gold standard in terms of what your basic standard comparisons of real versus fake should be. So here's real versus synthetic of blue and orange, and see how well they're pairing up on the different features, EKG findings, ST slope, heart disease, cholesterol, glucose, all of that. You can see similar things around the distribution of the data itself, also QQ plots. So various things that we kind of like complement each other that we typically would want to see within these studies. And then a lot of people like to just see the overall mean and standard deviation between these. And you can see that they're nearly identical from that standpoint too. So this one looks like a very nice validated model that you can now see how well it's done. On the training, it gave you an ROC of 88 almost, or 87.76. And it was on a KNN model that it built it on. And on a generalization, it was 90 on the synthetic data. On the tertiary, it was 88. So the likelihood of you having something by chance that are nearly identical ROCs on 3 separate things is pretty low. So then you can feel pretty good that you can actually go live with this, and you can now download it, and now you can go live with it. And here's now the heart disease S for synthetic that the investigator can have access to and can start doing a quick little pilot study and see if that's where basically if their study is worth pursuing further or not. And so the unique aspects of it, the end result gives you a most realistic validated synthetic data. And that basically that emulates the real data machine learning performance. And it's important to know that it's an on-prem platform from a data security standpoint. It's been validated on a large number of data sets and studies, and this is and it's also both binary and multi-class platforms. And here's a good example of like on 2 separate things. Here's now diabetes, where it shows you compared to real data, it has to happen to be a non-neural network Gaussian copula that was the best, synthetic data generator. But when we do it in, let's say, breast cancer study, we find out that it's a neural network-based copula GAN platform that gave us the best model. And so again, you don't know which one fits your data the best and which transformer is the best one for your particular, or let me say generator is best for your particular synthetic data generation. So how does this thing help our current landscape? So the current landscape versus our future proposed Sting landscape. The current landscape with no Sting, somebody has a brilliant idea. They now say, I want to get access to the data, but they know there's going to be a major climb in terms of waiting for paperwork and IRB and all that to get months of waiting before they get the data. And we all know that the likelihood of a lot of these studies pursuing is lower now. So many ideas may die. Versus in the Sting era, you could have the idea basically being generated synthetic data immediately for the person with a lot less IRB oversight because we're dealing with fake data. And now that data set can now be passed on to the investigator, and the study can get started, and we can actually enhance patient care potentially much faster. But outside of that, you can also argue that it's great from the current approach within the no Sting platform is you have partners and customers who come in and they may want to do studies with you as an institution. And how do you get the data? There's all sorts of regulatory measures around this. So most of these industry partners and other institutions won't even pursue such things. So there's potential loss of collaborations and loss of income to various institutions. But within the Sting platform, you can now, those same folks can come to the table. Not only they can get newly generated synthetic data, but now let's say you've been running this for a couple of years, you may have a few hundred synthetic data sets that are in your synthetic data biobank. So that synthetic data biobank could be a way that you could basically help give access to these things to your industry partners, which could mean that increased collaborations, increased studies, great for rare disease studies, for example, and so on and so forth. So in summary, Sting drastically lowers the bar for access to synthetic data, dramatically expedites the pilot study timelines, encouraging more pilot studies to be done within institutions, just transforms the way we're going to do future studies within these space, and increases interinstitutional collaborations, but by also creating large data sets of like synthetic data biobanks that could be shared or actually collaborated with your partners. Here's my Sting core team that I'd like to thank. And thank you for your attention, and happy to take any questions.
Yeah, that's just amazing. The only thing that stings me is like, where has Sting been? Like, it would have made my life so much easier, I think we'll take the questions at the end. We're right now a small group, but that was just fascinating and amazing. I think perfect time to transition to Rama. Rama, do you think this is ethical?
I can stop sharing, right?
Yes.
That was a great talk, Hooman.
Thank you.
That was
So much.
absolutely fantastic. I do have questions of my own that I would love to kind of talk towards the end. So I'm going to talk a bit more about a larger scale issue that I think is of importance within the practice of pathology, which is related to AI ethics. The way I came about to being interested in AI ethics is I've always had an abiding interest in philosophy, but I very quickly learned that it doesn't provide too much of income, which is why I kind of shifted away from it as quickly as I could. But it's kind of had a resurgence of interest, especially in the past decade or so. And I think it's an area and field that impacts a lot of healthcare, and we would be wise enough to kind of get up to speed on it and try to implement it. And that's basically the message that I want to convey today. I have no disclosures to make. So the outline of talk is going to be in this manner. We'll talk briefly a bit about AI in pathology and big data. It's probably one of the areas that AI has begun to make quite a bit of impact, and there is a lot of interest in the use of healthcare data by AI and machine learning scientists, mainly because a lot of pathology data tends to be well structured as opposed to clinically facing specialties whose data probably is a lot more unstructured. That's not the case in pathology most of the time. And it's a very image-rich specialty. We'll briefly talk about biases. How does one go about developing an ethical AI perspective? Regulation and governance is a big deal, which is changing. And what is the role of pathologists itself, and wrapped up with some conclusions. That's a lot. I won't be talking a lot. This whole area and topic is a huge one. The field of ethics itself is pretty expansive, but the field of AI ethics in particular is also beginning to kind of expand to areas and limits which are hard to keep a track of on a regular basis. So AI in pathology and big data. So what's the big deal? So data is the new oil that is running a lot of different specialties, pathology included. Traditionally, the role of pathologists has been one of diagnosticians. It's a big black box. Many times our own colleagues who are physicians in other areas don't really understand what goes into the process of diagnostics per se. It's a big black box for them. But increasingly, I think this will change into a role where pathologists are not just at the diagnosing end, but instead become information managers. And mainly the reason is because of this. We sit on the results of a lot of patient-related data that are actionable. And I'm talking about histology, increasingly molecular data, And when you combine that with the clinical and lab data in a temporal manner with AI models, what you have is essentially the future, which is multimodal diagnostics, where patient outcomes are dependent on a lot of the pieces of these data coming together in a seamless way. So within pathology itself, there have been a lot of applications. One of the biggest ones is, of course, classification tasks, where you have a histopathology image, a surgical pathology looks at, renders his expert opinion and diagnosis, and that's the way it's been for well over 100+ years now. But increasingly, the idea is to bring in an AI algorithm which is capable of looking at this and then identifying a diagnosis, basically classifying it according to a particular disease label. The other area where there's been a lot of interest is the automation of a lot of routine tasks, which can save pathologists time. In contemplating what goes into a diagnosis, there are a lot of routine tasks which people are not very well aware of, like counting the number of mitosis in a cancer field, or identifying locations where there is perineural invasion, detecting bugs like H. pylori. These take a lot of the pathologist's time. And the idea is if you are able to automate that in some manner or fashion, that will save a lot of time, improve the quality of diagnosis, and so forth. Beyond that, there is also a lot of interest now in seeing whether AI can enable complex predictions. And I think this is not just in pathology, it is everywhere. That if you have a different types of data, different sets of data whose origins are not necessarily the same, is there a way that you can integrate all of it and enable a much more accurate and robust diagnosis? Previously, until now, even now, it all is essentially what is going on in a physician's head. He is the one who is supposed to collate all of these disparate pieces of information and render a diagnosis, render a treatment, and so forth. So within histology and pathology in particular, nowadays, people are trying to use histology images not just to identify what's on there, but also predict things like molecular profiles, like does a tumor have microsatellite instability? Can we identify specific mutations, and so forth? So this is something that would be above and beyond the human capabilities of identification, at least in a way that we still don't understand. You cannot have a pathologist look at a slide and predict whether it has a mutation of this kind or that kind. And somehow, the deep learning networks seem to be able to do it. So obviously, pathologists are missing some subtle features that are embedded within a pathology slide, which the AI is able to pick up. So the majority of pathology-centric applications thus far have used imaging algorithms, not surprisingly, like convolutional neural networks, which have been amazingly successful in terms of doing predictions and so forth. But I think that is a very limited perspective of where this field is at. There's a lot more that I think can be done within the context of use of deep learning methods in pathology. So it's not just surgical pathology. They often get a lot of the focus and attention, but molecular genomics increasingly is a very powerful paradigm. So the ability to go beyond visual representations of a tumor on an H&E slide by actually looking at the molecular makeup of a tumor. That's what I'm a specialist of. I am a molecular pathologist. We do DNA diagnostics, RNA diagnostics, use of high throughput sequencing methods like next generation sequencing to build profiles, molecular profiles of what a patient's cancer represents or is trying to inform. But trying to combine these two with genomics and imaging AI models, I think is the next frontier where a lot of the power that exists within these algorithms is going to be unlocked. And not to be forgotten is also clinical pathology, which is a lot more lab-based diagnostics. So clinical pathology, lab diagnostics, like your routine CBCs and chemistry panels and so forth, represent a temporal profile of a patient's disease process, evolution, and so forth. And I think it's a great opportunity to be able to build in those temporal kind of patterns into an AI algorithm. So biases within healthcare and pathology is a big deal. I think in our attempts to run the best next algorithm on a set of data, we forget that our limitations within our biases are quite extensive that we still don't really understand. So I'm not sure how many of you guys know this, but there is this cognitive bias index. It's a diagram of Wikipedia. There are well over 170 known human biases in the way we think and assess. A lot of those biases are very specific to particular things, but the core ideas is that they boil down to 4 different things. We often trip up in our ability to understand and interpret things because we don't know what we should remember. There's often too much information, there's not enough meaning, and there is a need to act fast. And just these 4 core areas in a nutshell represent the current physician state of mind. They are just too many things to remember. There is very little time. We don't understand it all, and we have no idea what is of importance. So in AI algorithm development, cognitive biases are basically systematic patterns of deviation from the norm and or rationality in judgment. Pathology and medicine in general, we rely a lot on pattern recognition and heuristics. And these are the rules of thumb that help us achieve the kind of speed and turnover that we need on a routine basis. But equally, the problem is that these biases, the potential for these things to get embedded within a healthcare AI algorithm is non-trivial. It can very easily creep over into a training data set and then propagate down on and so forth. Computing power nowadays is pretty cheap. So anyone and everyone has access to algorithms, software to kind of run these things. But I think it's very important to understand we are fundamentally limited at a cognitive level, and we are prone to a lot of biases. So the algorithm, just mere performance on a test data set doesn't necessarily imply that it has a real world performance that would be similar and so forth. So this is where trying to understand the idea of ethical AI becomes very important for healthcare workers and practitioners in general who are trying to bring these things online. Poorly designed studies can lead to poor health outcomes, right? It's not a big kind of surprise there. But the question is, how do we address that? And that is not trivial. So here I'll talk a bit about the path forward. As I mentioned, the area of AI ethics is a vast and expansive one, and we do not have any concrete, meaningful paths forward that are well established and so forth. All of this is in flux. A lot of it is still being understood and so forth. But there are some key and fundamental, I think, ideas which are universally applicable. There is this author, Dr. Virginia Dignam, whose book I really like. It's about responsible artificial intelligence. She basically describes it as innovation process that takes into the effects and potential impacts on environment and society. In that context, for AI, I think there are three key principles that are of importance: accountability, responsibility, and transparency. There is this other book, Oxford Handbook of Ethics of AI. It's a massive tome of 800 plus pages. It's my go-to book for all topics on ethics and so forth. These are, I think, universally applicable in the context of pathology AI as well. So accountability refers to the requirement for the system to be able to explain and justify its decision to users and other relevant actors. Very key and critical component within the context of healthcare AI development. Responsibility, on the other hand, is the role of the people themselves in relation to AI systems. So as many of these systems come online, the developers on one hand have to have built-in systems for accountability that they are adhering to right from the get-go when they are trying to develop these systems. Responsibility, on the other hand, implies the role that we as physicians have towards implementing these novel technologies within the context of our own practices. It would be great to have guidelines for all of these things. Sadly, we don't have it yet because this is such a newly developing field. Finally, transparency checklist. Professor Dignam comes up with her own transparency checklist of what constitutes a good checklist for AI development. But I contest that this checklist for transparency is something that needs to be unique to each of our medical specialties, focusing down on the exact needs and requirements of the specialty that we all practice in, which means there is a real important role for all physicians of various specialties to identify what sources of bias might exist within their practice, consider those while trying to implement and develop these algorithms, and finally be on a proactive lookout for these issues once it is it's implemented and is in use within your own practice. Because at the end of the day, the responsibility and onus is finally on the physician, not on the algorithm, the way the laws are currently present. So this leads to the topic of regulations and governance of AI. Where are we at this point? Sadly, not well ahead. There is this book of Artificial Intelligence for Better Future by Dr. Stahl that I like a lot, which tries to basically discuss the key players within the regulation process of AI, which involves governmental lawmakers at a high level. Organizations themselves are very responsible. So this means your own hospitals are to some degree liable for the kind of AI that they try to bring in. And finally, individuals, physicians, healthcare workers, all of the experts who are trying to develop AI also have an active role to play in all of this. He describes a very detailed checklist of who are all the players and what their roles are and so forth. EU, interestingly, is taking a big step towards finally regulating a lot of AI intelligence with their new AI Act, which has come about in the last month or so. The compromise text is still being evaluated, but EU has definitely been a proactive player in trying to develop regulation for AI. But that came about because they have been actively working at this for a very long time. They have put about requirements for human agency oversight, what constitutes technical robustness, safety, data governance, and so forth in a very detailed manner, which I think has been at the forefront of what a regulatory strategy for AI in general should be. And they are finally at a place where they are beginning to implement laws that I think will affect AI research and development on a global basis. In the United States itself, there was a recent AI Bill of Rights proposed by the White House, which I think is going to be a good blueprint for where we are going in this domain. There is also the Algorithmic Accountability Act of 2022 that was proposed and still making its way through the legislation. So overall, United States has been a bit of a laggard when it comes to regulation, but that's also because a lot of the active AI development is probably taking here in the US and also China. At a society level, the College of American Pathologists, which is my parent professional organization, has been very active in driving the AI implications within pathology. There are multiple committees. There is also a CAP AI ethics working subgroup of which I'm a part of. And we are trying to come up what are the guidelines for the implementation, use, and as well as utilization of pathology data in general. So there should be, I think, every specialty should have these kind of initiatives to drive what constitutes ethical usage of the data generated by within that specialty. So what role do pathologists have in ethical and explainable AI? Now, explainable AI itself, for those who don't know, is a full-fledged field in trying to make the process of AI explainable in a format that you can predict why a decision was made by an algorithm. Of course, it is a lot easier when you had simpler algorithms, though very efficacious algorithms like regression classification, which were the initial kind of machine learning algorithms that were put out there. But it's become a lot more difficult with the new versions of algorithms like deep learning and so forth, where it's basically a black box. I mean, I hate the term, it's a black box, but to be honest, it is a black box that we don't quite understand what goes into the fine-tuning of the weights that happens at different levels, different layers, different nodes, and so forth, like that, which are key to the final outcomes that are generated by an AI. We really don't have any understanding of it, I would say, at this point of time. But all of those are trying to be understood within the context of explainable AI. So, but again, there is also this pushback of the driver analogy, right? To drive a car, you do not need to know how a car is built. You just need to grab the wheel and drive. So, but does that really hold valid within the context of AI is a different question, especially in an area like healthcare, where people's lives are at stake, depending on the interpretation and usage of an AI algorithm's output. For me, my own personal vision of what constitutes explainable AI within pathology is something that can account for a lot of different things, like model performance, explainability, give me as a pathologist an output confidence of how confident the AI is about. Also incorporate data from multiple modalities within pathology based on principles of ethics and transparency. Unfortunately, bringing all of these elements is a very tall order and not anywhere near close to being possible. So I think there is a lot of synergies that are possible to create such an ethically enabled future of AI. Pathologists themselves have a lot of different skill sets, pathobiology, domain expertise. We are well trained in integrating a lot of different kinds of modalities, data, clinical pathology, molecular pathology. We are good at understanding biases and so forth. QA/QC is also our bread and butter for a lot of things. Computer scientists are very good at algorithm development, data analytics, and so forth. I think there is a lot of potential synergies to create ethically developed AI by talking to each other. So within pathology itself, I think there is a ton of opportunities. Human-computer interaction studies, policy development, all of these fall under the key domain of what is called as ethical AI now. And there is hardly, I think, anyone who is working on these topics at this point. So in conclusion, ethical AI development of AI is a huge and hot topic, not just in pathology, across the entirety of healthcare, and also in other specialties, and definitely includes the need to bring a lot of people together at the table to make it happen. Unfortunately, right now, most of the ethical AI research is driven by computer scientists who focus on technical ethics, or professional ethicists like philosophers who are more aware of things like moral ethics. The missing piece, in my opinion, is the domain expertise voice of physicians themselves. We have to be at the table and join in this conversation while these healthcare AI workflows are developed. If you're not at the table, you will be on the menu. So, that's something that I think we should all be aware of. Medical professional organizations, I think, have a huge role in developing the guidelines and oversight and so forth. And for pathologists and physicians in particular, I think it's important to acquire the knowledge necessary for the implementation, evaluation, and assessment. So this involves necessarily understanding, at least at a very basic level, how things like data analytics work and so forth. I mean, you don't have to necessarily be a programmer, though it can help, but you have to have at least a high-level understanding of how a lot of these things work. Here are a couple of papers that are focused on AI of ethics in pathology in particular. This one is the one that I co-authored with a colleague, Dr. Chavi Chauhan. And here are some healthcare ethics topic ideas that I have been kind of looking at and trying to understand and so forth. And here are my references. And I'm glad to take any questions.
Well, thank you, Rama. that was like amazing and very thought-provoking. I think we are just getting started with this, as you said. Yes, a lot of work has been done around the technical side, but we are trying to see how we absorb that on the clinician side, and ultimately we are the ones who are responsible for delivering care to the patient. So we have to lead this work for healthcare. Dr. Rashidi, I saw a question from Burke over here, which was around like digital twins. So that concept has been around for a little bit.
Yeah.
And his question was around this digital twins concept and how can you use synthetic data for that? Let me try to get the exact question. How about digital twinning with synthetic data, also incorporating genomics?
Yeah, no, that's a great point. So actually, for those of you who've studied that, you know that the folks who are doing digital twinning, they have some synthetic data generation, element in it, right? In terms of the pipeline. By the way, Rama, that was a beautiful talk. I'm definitely want to steal your presentation. So, I'm definitely not well versed in that part, so you'll have to teach me about a lot of these things. But very thought provoking. I loved it. So going back to the digital twinning and synthetic data. So I mean, this is literally in its infancy stage right now, right? The stuff that we're doing. There's lots to learn, lots to kind of understand, lots of oversight to have. I have to say, I'm more on the cautious side of things in terms of both access to the stuff and just as importantly, applying the stuff. But there is a lot of potential opportunities. One of which I didn't go into for time reason, one of which was like for within our platform, when people build synthetic data, and I'm glad, Burke had asked a really nice question, which was you build, let's say, the synthetic data, and you really go after the one that was the best one for, or the closest one to your real data, right? And that people ignore the other synthetic data sets that could have been generated that are not as good, but just as valuable if you want to do a simulation study. So because within, as opposed to like image data, deep learning platform type studies where we do see, data drifts and deterioration of models, but they're not as drastic as tabular data, where it's just part of our day-to-day operations. We know when we build a tabular, any kind of a model, ML model, we know that, let's say if I built an ML model around sepsis and it was trained on a particular bug and specific antibiotic resistances that was in our EMR now, let's say in a year, that could be completely different population, or maybe some major event happened. And all of a sudden that sepsis model is no longer, even if it was beautifully performing, will no longer perform down the road. So having a way to continuously upgrading your model, make sure that's part of your ML ops, is extremely important. And I think the synthetic data, not only the good counterpart, but more importantly, the ones that, like within Sting, we give you like 8 different synthetic data generators are giving you different synthetic data sets, right? One of them happens to be nearly identical to the real data in terms of performance. But instead of devaluing the other ones to say they're not worth anything, I personally think there's a lot of value on something else that might be 80% as good as the original real. Because then if you're doing a simulation study, you may be able to incorporate that and be able to predict drifts that could happen, or what a drift could look like in a simulation study when you do encounter it. Because you can kind of like almost a prediction of another prediction, kind of a double prediction, But that's a very interesting point you bring up. And I think I'm 100% in Dr. G's camp, which is that right now we're in infancy stage on a lot of these things, because let's face it, we're typically especially within healthcare space, we're in this single modal path. But as more and more people get used to this space, and more importantly, more and more data becomes available that can crosstalk, then, as he said nicely, the near future is going to be multimodal, especially now that we have access to foundation type models where we can handle things like that. So in the future, and it's not a foreign concept to us. I mean, maybe it sound like it's a really drastic thing, but we've been doing similar stuff. It's just been titled something else. we call them ensemble algorithms, or, I mean, obviously they happen to be in the same data typically. This just happens to be different data. So just like, or it could be a combination, a multimodal also could be a combination of, a smart tool like human-based rules combined with a couple of different models from different data sets, But yeah, there is lots of advances in that, and I think all of that will help. I just think synthetic data is going to be a nice complement to a lot of these things. The biggest reason I was going after the synthetic data and built Sting, it was because of my own pain points. It was just that waiting for months to get, your data sets, just the excitement around the study goes away. And more importantly, it's no longer about me. It's more around, imagine how many brilliant ideas, and we kind of have, we're kind of lucky in our field in medicine. I mean, you have this selection bias, around people you've picked to come into medicine, and these were done through tests and whatever else, right? So these are bright people who basically you've now picked out from the population as a whole, generally speaking, who now they are doing their current task, but then they may not be as excited about doing particular studies because they all of a sudden think about all the hurdles they have to overcome with the IRB. So if we find ways that could basically, decrease that barrier and get them easier access to the data for a pilot study, we could transform the way and expedite the way we do things for our patients, and just really, really change the way we do quality studies and the way we do research studies and so on and so forth. I don't necessarily think that it applies to everything. I definitely think there's limitations, and just like any tool, there's limitations in it, but it's just one of many things that we could kind of incorporate as we kind of dive into this space.
No, those are some great thoughts, and looking forward to using Milo and Sting in the near future and collaborating with you, just like I'm sure others are over here and others who will be listening to this too. But Rama, I have a question for you. So it's a hard time, it's a little bit hard for us to grasp the idea that, there are these models that we can't explain that are a lot of times built on real data. And then you put in things like synthetic data, and then you put in things like Auto-ML and your models. And then those are supposed to make predictions which we are going to use for patient care. Thinking about that challenge, how do we overcome that to help our clinicians so that they can impart confidence in these predictions as they deliver information to our patients? Right. Do you think that requires a completely separate set of ethical principles, or do you think that needs a separate set of educational efforts for clinicians so that they understand it better and they are able to explain it in a better way?
So here's what I think. So I think it is all in that right now, the way we have AI research going on in the healthcare space, at least the way I look at it is, you have a model test data set, you run your algorithm, you get a accuracy of 0.9 above and so forth. That doesn't really transfer, I think, well enough into the real world. We need to have better ways and means and processes in place to bring about all of these algorithms to have the kind of weight of evidence that it requires before it actually can implement it. Now, that is a task that we as individuals cannot do. Then I think it falls upon essentially institutions to have their own principles of guidelines as to how they assess AI algorithms before they bring in-house. And also these will be built upon what I think will be the general law and regulations that are established at a national level. At the same time, I think it's also critical that we improve the educational processes that we have for physicians. The current model of pathology is still the very old and stodgy model where you sit at the microscope with a seasoned pathologist, and there's nothing wrong with that. I mean, we are talking about a model that has worked for well over 100 years. But times are changing, data is coming on at a very fast speed. the kind of modalities that can generate data that are meaningful for a patient are also expanding. And so the educational setup, I think, needs to be geared towards being able to integrate all of those, at least have an open mind to kind of bring those techniques and methods on and at least impart it for the next generation so that they're ready to go. I'm heartened to say that there is a lot of different mindsets in the next generation of residents and fellows that I see. They are much more willing to learn new things and take on this. But I think it's a community effort. We're not escaping that fact.